All right, we're going to attempt that chapter 7 thing again because last time we got no audio. So I checked and we are getting audio this time. We started with 7.1, where we learned that if I were to take any triangle, it can be a right triangle, equilateral, isosceles, doesn't matter, and draw in one side, which is parallel, drawing a line which is parallel to one side and goes through the opposite vertex, I end up with these three angles, which I'll label with a hoop, a dot, and a notch. Well, due to the parallel lines, that one is congruent to this one, and this one is congruent to that one. So looking at the line, we see that a notch, dot, and hoop add up to 180. So a notch, dot, and hoop, hard to say, must also add up to 180. And we've just proved that the sum of the angles in any triangle add up to 180 degrees. There was kind of a corollary to that, which said that if we had an exterior angle, it was equal in measure to the sum of the remote interior angles. So if this were x degrees, this one would have to be 180 minus x degrees because they are supplementary. And this one plus that one would also have to add up to 180 degrees because they form a full triangle. So if this plus those equals 180 and this plus that equals 180, then those and that are equal to one another. In 7.2, we had a couple of theorems. The first of which was the so-called no choice theorem, which said that in two triangles, which clearly don't have to be congruent, if I know that this angle is congruent to an angle over here, and I know that this angle is congruent to another angle over here, then that third pair of angles needs to be congruent. Stated if two angles in one triangle are congruent to two angles in a second triangle, then the third pair of angles are congruent. Again, it does not imply that these triangles are congruent. However, our next theorem does. Our next theorem is AAS, the only theorem from the second semester to prove that triangles are congruent. So AAS says what you would expect it to say. It says if two angles and a non-included side are congruent to the corresponding parts of a second triangle. And here it's important. If I put one of the hash marks over here instead of over here, then they wouldn't correspond. One of my students is having a fire alarm going off at their house. No bueno. All right, these two triangles are going to be congruent, and of course that is through AAS. The last theorem before we jump into formulas, the last theorem from this section was that midline theorem, and it said that if the midpoints of two sides of a triangle are connected, so this has to be a midpoint and this has to be a midpoint, then the resulting segment is parallel to the third side and half of its length. Not particularly interesting once we start getting into similarity, because the small triangle here is similar to the big one, and the ratio of their lengths is just 1 to 2. So that one kind of goes away in terms of importance. Anyway, on to the formulas. And here are the formulas for the chapter, which hopefully are big enough for you guys to see, even on the standard definition recording of this. So these are the polygons which you need to know: triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, dodecagon, and pentadecagon. You should know what number of sides each of those has. Of course, triangle, like triceratops, triathlon, trihawk, any number of different things, has 3. And you can probably think of examples of all of them down the line. By the way, heptagon, also acceptable is septagon for 7 sides. And from there, if you know these formulas, the rest of it you don't have to memorize. So if you know the number of sides, you subtract 3 from that to get the number of diagonals which can be drawn from each vertex, different than the total number of diagonals. There is one more triangle than diagonals per vertex. So I could either subtract 2 from n or add 1 to the diagonals per vertex, get the number of triangles, which is important because that helped us to find the sum of the angles. Each triangle, all n minus 2 of them, give us 180 degrees. So if I take 180 and multiply it by my number of triangles, by that n minus 2, I'll get the sum of the interior angles. If they don't specify which angles they're talking about, they mean interior angles. The sum of the exterior angles, easiest question, is always 360, no matter what shape you walk around. If you walk around it, you turn 360 degrees. And this formula, probably the hardest one, n times n minus 3 over 2. Each vertex, and there are n of them, has n minus 3 diagonals coming off of them, but they're all kind of doubled up because when one goes from point A to point C, another one goes from point C to point A. Well, it wasn't really another one. It's the same one, but we counted it twice. These other two formulas here only work if the polygon is equiangular. If they tell you that the polygon is regular, that means that it is equiangular and also equilateral. So that is more than enough information if they say it's regular. So each exterior angle, well, if they're all the same, I'm going to take the 360 degrees and divide it evenly among those n different angles. So 360 divided by n. And there are two different formulas for each interior angle, but this is really the easier one and the one that I prefer. It's just supplementary to a exterior angle. So I take the exterior angle and I subtract that from 180 degrees. That allowed us to do the types of problems that we called muffin problems. If you recall, those are the problems where you ended up drawing a muffin looking thing because you weren't really clear on how many sides a figure had before you started drawing. You did have to recall that interior and exterior angles are always supplementary. That is it for chapter 7. Hopefully it recorded a little bit better this time around, and I will see you on chapter 8.